guys, and welcome to lesson 10. We're going to discuss higher order derivatives and implicit differentiation in this series of videos. So let's start. First, let's have the higher order derivatives. Okay, so what are higher order derivatives? Basically, if we have a function, our premise, we have a differentiable function. So there is actually an order in getting the derivatives of this function, and we are familiar with our function. Take note, we have three different notations. We have the Leibniz notation, we have the Lagrange notation, and we also have the y prime notation. Take note that the y prime notation is it's actually a version of Lagrange notation. Okay, so we write our function as either y or f of x or any variable that we use, like for example if it's a function of t, or if it is h of x, h of t, so on and so forth. But in this scenario, we're going to use y and x as our variables, our dependent and independent variables respectively. Okay, so getting the derivative of the function y or f of x, we get the first order derivative, and the first order derivative is written as dy dx. So we have the Leibniz notation, and we're very familiar with this if you have watched my previous series about the basic differentiation rules. Then we have the Lagrange notation. We have the f prime of x. Okay, we have f prime of x. It's read as f prime, like Optimus Prime of x. Okay, and then we also have the y prime. Okay, for the y prime notation, we have y prime. So f of prime and y of prime is almost similar in its definition, but take notes, in y prime you must look at the given variable also to know what variable is the function being differentiated to. Okay, also after the first order derivative, if we try to get the derivative of the derivative, okay, we'll get the second order derivative. So we have here the 2 here. Take note, this is not exponent. Actually, this is not an exponent, but rather a notation indicating that this is the second order derivative. So we have the second order derivative of y with respect to x. So we have f second prime, okay, and then we have the y second prime, okay, or sometimes it's read as f f double prime or y double prime. Okay, so either the ranking f second prime or f double prime, or y second prime or y double prime can be read as that. And of course, if you have the third order derivative, if you get the derivative of this derivative of the derivative, you have the third order derivative, you have the f third prime or f triple prime. You can also have the y triple prime or the y third prime, and the third order derivative. So in general, it's an nth order. We have this, so we have the n as our placeholder. Okay, and take note that for the Lagrange and the y prime notation, n is written in a Roman numeral. Okay, so for example, if it's fourth prime, so we have f the fourth prime, and we have y to the fourth prime. Okay, f to the fifth prime for the fifth order derivative, so on and so forth. Okay, so let's continue. Let's have an example. So for example, we are asked to find the third order derivative of the function, and we're given this function here, y equals 2x cubed plus 3x squared plus 2x plus 1. So for us to get to the third order derivative, we must pass through the first and the second order. So we get the first order derivative. By the way, I am using the Leibniz notation, dy dx, because that is the standard. Okay, so for our course, our standard will be dy dx unless it is given as f of x or so on and so forth. But it does not actually matter as long as you understand your answer, that we will always get the same answer anyways. So we have dy dx being 6x squared plus 6x plus 2. We just got the derivative of y. Okay, and then we will get the derivative of this dy dx. So we have now the second order derivative, which is 12x plus 6. And finally, getting the derivative of this second order derivative, we'll get 12. And this is our final answer. Let's have another example. For example, you're asked to find y double prime, okay, of the function y equals tangent of 3x minus 1. So, of course, we'll start with y prime. And take note that the derivative of tangent is secant squared. And of course, there is the derivative of the inner angle, which is 3. Derivative of 3x minus 1 is 3. That's why we have 3 secant squared of 3x minus 1. And then we'll get the derivative of this derivative. We have y double prime. So, to get the derivative of our derivative, so we will use scalar rule. So, as is, 3 is as is. Then, use power rule for secant of 3 of x minus 1. That's why 2 is here. Then, minus 1 for our exponent in secant. And then, we'll get the derivative of secant. Okay, because this is chain rule. Okay, take note, chain rule. Then after getting the derivative of secant, we know that the derivative of secant is secant tangent. So we have secant of 3x minus 1 and tangent 3x minus 1 here. But there is also the derivative of the angle, which is 3x minus 1. Okay. And lastly, getting the derivative of the angle, 3x minus 1 is 3. And then rearrange, we have 18. Okay, so we combine the two seconds here because they have the same angle, 3x minus 1. So we have 18 secant squared of 3x minus 1 tangent 3x minus 1. Okay, next, let's have another example. So we are asked to find the f to the fourth prime, f to the fourth prime of x at x equals 1 of the function y equals to x plus 1 all over x. Okay, so we'll get first the f prime of x, which is quotient rule. We apply quotient rule here. Okay, and applying the quotient rule, we'll get negative 1 over x squared. Then f double prime, since negative 1 over x squared is also a quotient, or rather a rational function, so we'll get the derivative of that, which is 2x over x to the fourth, which is 2 over x cubed. Okay, then we'll get the f triple prime, or to the third prime. We have this, and then we simplify. We have negative 6x squared over x squared, which will give us negative 6 over x to the power of 4. And lastly, we are going to find, okay, so we'll start with this, by the way. We're going to find the f to the fourth prime. So, yeah, that's it. So, since it's quotient again, we can apply quotient rule, which will give us 24x cubed over x to the power of 8, which is 24 over x to the power of 5. Take note that we are given x equals 1. Hence, we're going to substitute that to our derivative, okay, our f to the fourth prime. So we'll have f to the fourth prime of 1 equals 24 over 1 to the power of 5 based on this, which is just 24. And that is our final answer. Okay, so in the next video, we're going to discuss implicit differentiation. See you there.